I looked back, and the last time I was here, even though we're not very far away at Swinburne, was 2019. Of course, there's a thing that happened in between those years. I didn't come here as early as I would have liked. But I did actually talk about this topic then because it was just starting as a project. And I was very excited about it, but I didn't have any real results to show, and it was a very short talk. But now I can actually show you a whole bunch of results that we've got from this, and even the next phase of it, where we can start to use this stellar twins technique that I'll be talking about to really probe quite distant stars where there's a lot of dark matter in our galaxy. That's the main idea. So there's a lot of collaborators here. Mainly, a lot of the work I'll be showing you was pushed forward by Daniel Berkey there on the left. Ben Scott has sort of taken up the mantle of that work using solar twins, so stars like our own sun. Brett Addison and Fan and Chris here have been working with me on trying to use the same techniques for different stars, giant stars called red clump stars. So I'll be getting to those later in the talk. I just want to acknowledge there's a lot of men here. There's no women in our collaboration at the moment. So lots of effort has been put into trying to attract some non-male participants to this work, and we'll keep trying, but that you can see that that's a definite difficulty in our field. So what will I be talking about? When I say testing fundamental physics, what do I really mean? I mean looking to see whether the fundamental constants of nature are actually the same or whether they vary in some different places. Now, by places here, I don't mean necessarily in different places in space, but in different parts of parameter space. And so that's where I'm getting at that second bullet point. Where should we look for these variations? That's a very important point, and I want to really press that here. The main thing I want to address is, can we look to see whether electromagnetism and the strength of electromagnetism, it's a fundamental constant. Does it actually vary with dark matter density? Are these two things somehow connected at some much deeper level, not just electromagnetic interactions with dark matter, but are they connected at some beyond standard model level? And that's really what we're trying to probe here, is the physics beyond the standard model. So the project, more specifically, is to try and map electromagnetism strength across our galaxy, particularly where there's a concentration of dark matter density towards the center. We've already done the initial work showing that this really does work with solar twins. We're moving to a different type of much brighter star called red clumps now, red clump stars, and we're actually starting the observations for those very distant stars now on two different telescopes, the Very Large Telescope in Chile and Keck in Hawaii. So the fine structure constant, this is the coupling constant, the strength of electromagnetism. It's obviously got to do with our relativistic quantum mechanical electrodynamics theory. So those three very familiar numbers all combine together to give you this dimensionless quantity alpha, which tells you the strength of the electromagnetic interaction. We think that that's a constant, but why? We write it down in our textbooks as a fundamental constant, but why do we do that? And I want to explore that by making this plot. And this is where I really want to be in 3 years with this project. I want to be able to look for variations in alpha here. This is in relative variations in units of parts per billion on the vertical axis as a function of this distance from Earth. So I want to look much further away from Earth where we have a larger concentration of dark matter. This is how much more dark matter there is compared to what we have here at zero distance from Earth, where it's 1 on the top scale. And what we know about galaxies in general, but we think we have observational constraints in our own galaxy, is that the variation in dark matter density really scales up as you go towards the center of our galaxy. And so if the fine structure constant varies according to that, or maybe just it varies in some other functional way, but much more where you have a larger dark matter density concentration, then you should see these data points here that I've put in bins of 1 kiloparsec deviating from 0. If we don't see any variation in alpha, they would all be sitting down at 0. I've just put them on that Navarro-Franken-White dark matter density profile for fun, but also the error bars here are the most important thing when projecting an experiment, and these are realistic, and I'll show you why that is later. So that's where I'm going with this talk. That's where I'm going with this project. That's really the plot that I'd like to see at the end. So why do we think alpha is a fundamental constant, or any other what we call fundamental constants? Why do we think they're fundamental? Well, it's sort of a bit embarrassing. We call them fundamental because we have no idea what they are. Now think about that. It's very strange, but we sort of give them this lovely name, but we don't actually know anything about these numbers. We have to go into the lab to measure them. The theory itself doesn't tell us what they are. It doesn't tell us their value, it doesn't tell us that they're constant. It just says they're a parameter that you have to put in to make the predictions of that theory usable. So you have to go into the lab and measure them. And this is a big hint, and it's been recognized for more than 70 or 80 years, that this is telling you that the standard model is at least incomplete. And it's probably telling you that the standard model is not the most fundamental theory of physics. We sort of know that for other reasons as well. We kind of suspect, well, we know it doesn't explain gravitation, for example, and we kind of suspect that it should. That is, that the most fundamental theory we can come up with should explain all the fundamental interactions that we see, but this one certainly doesn't. And this is another big hint that we should be looking for other physics. And why do we think it's constant? Well, when we do go into the lab and measure this thing that we need to have in order to put into our theories, we find that it doesn't vary much. It's another reason why we also say it's sort of fundamental. We don't find that it varies, and in fact, people spend a lot of time looking and making sure that alpha really is constant in laboratories on Earth. And some of these are the most exquisite lab experiments I think you can find, where you get down to precisions of 3 × 10 to the minus 19 per year. These are sort of 1 or 2 year long experiments where you compare different atomic clocks that tick according to the transitions in different atoms. That is, for example, aluminium versus a mercury clock, for example. If the ticking of those two different clocks started drifting from each other, that should be a mark of a variation in alpha. But we don't see that. So we've tested this, right? We've tested it in the lab. So we can stop there, right? It must be constant. No, people keep looking. Why do they keep looking? Because we don't actually have a theory to tell us how much it should vary. It's not surprising. We don't have a theory to tell us what the number is either. So if you want to find the keys to the next most fundamental theory, or the most fundamental theory, the keys to the universe, you need to look under lampposts. This is a reference to this sort of silly story of a drunk trying to find their keys after dropping them somewhere in the dark. Where should they look? They should look under a lamppost because that's where they can see. We look in the lab because that's where we are. That's where we can do a very good experiment. That's where we can see. But astronomy, and I think this is a point sometimes missed in Australia, astronomy has kind of a really great view of the universe where we have a whole bunch of other lampposts that we can look under that we do not have access to here on Earth. And it's sort of our responsibility to do fundamental physics experiments in astronomy because we have access to these. I think this is a point really well accepted in Europe, but not as well accepted in the US and here. And I do like to push it a little bit because it kind of gets people thinking that, yeah, that astronomy should be used for this as well as finding out about all the things in astronomy. Jim Peebles, who's in America, realizes this as well, and he laments that America doesn't do as much on this, but he says, well, we also have a similar situation with dark energy. We look for variations in dark energy in its equation of state. We look for evolution in its equation of state with time in particular. We don't have a great theory of why that should be, but we still look for it because it tells us something fundamental about what dark energy might be, right? Because we don't know at the moment. But he says, well, it's equally good science, by the way, to test whether alpha varies. We know how to do it, and I've written lots, and other people have written lots about how to do it. So why isn't there a well-supported survey in astronomy for actually looking to see whether the fine structure constant and other fundamental constants vary? It's a good question, I agree with him. But he's talking about using these other lampposts that we have available to us, but which we don't really put much effort into using. So we have this great lamppost here on Earth with staggering precision, can do great experiments, but it's a tiny, tiny bit of parameter space. 2-year experiments in our own Earth is a very tiny part of the universe, And you might suspect, well, okay, maybe let's look over a much larger distance range, a much larger time range to see whether if we have variations in alpha or other constants. And so I think the most precise way to do that at the moment is something I've been working on for a long time, is to do quasar spectroscopy, where you look along the line of sight to some background quasar, a nice bright beacon for light, and that light travels through a distant gas cloud or clouds along its way to Earth. And that's where we're shining our lamppost. That's the thing we want to study, because it imprints nice, narrow, sharp absorption lines into the spectrum of that quasar. And we can use the relative spacing between those lines, those metal lines, as a mark of the value of the fine structure constant in that cloud. So all we need to do is compare the spectrum of this cloud to the spectrum of those same metal lines here on Earth, and we get out a value of how much alpha has changed, delta alpha on alpha. If we do that, and we've been doing that for quite some time, we know how to do it really well. I think we've kind of almost got to the limit of what we can do. We get down to about the 1 part per million level. So that's an astonishingly good and precise measurement in astronomy. Does anyone else measure anything to 1 part per million precision here? No, it's extremely good. That's why. Why is it? It's not because we're really good at it. It's because of spectroscopy. That's the key thing here. Spectroscopy is one of our most precise tools, both in the laboratory and in space. So we've looked over long cosmological times and distances. We haven't found any variations. What about other lampposts? We have access to places where there is a much larger gravitational potential. Here on Earth, we don't have much, but here around white dwarfs, we have about 10,000 times the strength of the gravitational field. So if you take a spectrum of a white dwarf, sometimes you see some metal lines in their atmospheres, probably the leftover debris of the solar system, of the planets and asteroids left over after it collapsed. But you can use the same technique. Look at the relative spacings of those metal lines in its spectrum and compare that with our laboratory spectrum of the same lines. When you do that, it's not quite as precise as quasar spectroscopy, but you get down to about the 10 parts per million level. Okay? So we don't see any variations in alpha at the moment with this. You might suspect, if we're trying to unify the standard model of particle physics with gravitation, this is a well-motivated thing to do. And indeed, there are specific theories which kind of bear that out, and I'm just giving the general motivation for that. But another thing where you can easily think, well, there must be a possibility of a connection between something we have no explanation for, like dark energy I saw before, and now it's dark matter, and something else we don't have any explanation for, which is the value of the fundamental constants and whether or not they vary. So you can ask, is there a deep connection between these two things? We should be looking for variations in the fundamental constants where there is a lot more dark matter, for example, or perhaps a lot less dark matter. But this is the question I want to focus on, and where I've turned a lot of my attention in the last couple of years or few years. So this is the idea. We have a lamppost in astronomy where we have a very, very big concentration of dark matter. Not so much around our sun, here at 8 kiloparsecs from the center of our galaxy. But if we go much closer to the center of our galaxy, at least according to most sort of theories, there is a larger concentration of dark matter, especially as we go inside the sort of inner 4 kiloparsecs towards the center of our galaxy. We don't really know whether this continues to go up within the sort of inner 1 kiloparsec, but if we can probe to sort of 1 kiloparsec out, 7 kiloparsecs from where we are roughly, then we can access dark matter densities that are 10 times higher than what we have around our Earth. So this is a good spot, it's another good lamppost to look under, and we think we can do that by using stars as our probe of the value of alpha in these different places in our galaxy. Here's a specific, I mentioned that there are specific theories that motivate these kinds of more general arguments that I've been putting forward. Here's just one, 2019. This particular theory assumes that there's a coupling between dark matter and, in this case, charged fermions, things like muons. This is very typical for a beyond standard model theory. You invent a scalar field and you prescribe how it couples to different things, and you explore what its experimental consequences are, and then you look to say, well, can we actually test that theory? They're not usually as popular, these kinds of theories, compared to the normal dark matter theories. you might know about, because they're not really testable at the LHC, right? You tend to get to know the ones that are testable on Earth, but you don't tend to get to know the ones that you can't, and this is one of them. So this one, the dark matter in this case, under this theory, changes the fermion mass, and that changes how alpha runs with energy, and indeed the other forces as well. And so what you end up with is that as you get a variation in alpha with the radius of the galaxy, here at about sort of 8 kiloparsecs, you can see you get a different answer to what you would get at, say, 1 kiloparsec out from the center. It actually has numbers on this graph. Those are kind of, you can dial those up almost arbitrarily, probably within a factor of 1,000 up or down, because the theory is very unconstrained by other experimental results from our labs, for example, which is precisely the point of why you want to test it in our galaxy and not in a lab. But we can actually test exactly this plot if we were to use stars as our probe of alpha in our galaxy. So how do we actually test for alpha? I've mentioned spectra a few times. I've mentioned the relative spacing between absorption lines a few times. And indeed, I'm going to explain why that is a good test of alpha. So the key thing to realize is that alpha sets many of the things we see around us, of course, in electromagnetism, but it also sets the scale of the energy levels in atoms, right? So here's a very simple energy level diagram. You've got an S-wave ground state and two transitions to two upper levels. They're really the same level, but they're split by the spin-orbit coupling, which is the fine structure splitting. It's where the fine structure constant gets its name from. So that's why I'm showing this very simple example. You see two different transitions in your spectrum, and you can measure their separation, right? You can compare that separation to what you see in the lab. That comparison is sensitive to alpha. Not surprisingly, it's the fine structure separation. This is a very simple example of how the two different transitions that you see there will vary as you change alpha. Really, it's the separation that you'll measure. This is fine and nice and simple, but it's a bit inefficient because this S-wave ground state is the level that has by far the largest relativistic corrections. That is where alpha comes in to the equations that govern the energies of these levels. So the electron's much more concentrated near the nucleus, basically, in an S-wave ground state, and so it's moving faster, if you like. It's higher, a much more relativistic system. Whereas these P-wave states, if you remember, are these kind of dumbbell-shaped orbitals where they basically spend no time near the nucleus, and so they're much less relativistic. So these two levels have this S-wave ground state in common, so its sensitivity to alpha is kind of removed from the equation in this case because they're both coming from that same ground state. What you'd really like to do is compare different atomic systems, different sets of energy levels, so that you can access the levels that have the largest sensitivity to alpha, right? That's not being done here, but it is done in what we call the many multiplet method that, my goodness, was done 25 years ago. So schematically, this is how you would write down the relativistic corrections for a many electron atom. The sort of general atom you would have in a star or quasar absorption cloud or something. And looking at the metal lines, you would say, well, there's a very strong dependence for a start on the atomic number, so how heavy the ion is. And so just immediately you can say, well, let's compare the same sort of transition, the same sort of orbitals in light and heavy atoms. So the transition from the light atom won't change much as you change alpha, but the transition from the heavy atom will change a lot. And so by looking at their separation, suddenly you've got a very sensitive system for looking for variations in alpha. There's also this other more complicated term, this roughly constant sort of C for these purposes is about 0.6. And so and this J is the total orbital angular momentum of the upper state. And so if you compare things like an S to P and an S to D transition, the sign of this whole term changes. So that is, you have one transition that shifts, let's say, to the blue as you change alpha, and another transition that shifts to the red as you change alpha. That can even be in the same ion from the same ground state. So by combining these sorts of effects for many different types of transitions, you get a very characteristic signature of a varying alpha. And we write that down in the end for astronomers as delta alpha and alpha, you know, the velocity shift we observe in a given transition in astronomy in our spectrum obviously scales with delta alpha and alpha, basically linearly. But you also need, if you want to know what that amount is, you have to actually calculate what Q is, and that's what we call just a sensitivity coefficient. Here's where all the quantum mechanics is. And you can't measure this in the lab. You have to go and calculate it from first principles in quantum mechanics to say, how sensitive is this transition to variations in alpha? How much does it shift to the blue or red as you change alpha? That's what this Q is telling you. If you measure a velocity shift between different transitions in your spectrum, that is a characteristic of a variation in alpha. But if you want to know by how much alpha has varied, then you need to know Q. Okay? So that's how it works in practice, and this is how it looks in practice. Is it going to let me do this with the laser pointer? Here we go. So if you have a laboratory spectrum where you have a bunch of transitions that you know their wavelengths, you can compare those to the same set of transitions in an astronomical target. And as alpha grows, you see those transitions all move in their own characteristic directions. And as alpha gets smaller, they move in the opposite directions. And that set of velocity shifts there is very characteristic of the transitions that you're using as your probe. So this is how we use spectroscopy to probe alpha variation. And this is pretty general. I mentioned atomic clocks before in the lab. This is exactly the same thing. They use atomic transitions in the lab and comparing different clocks ticking according to different atoms, different transitions. It's exactly the same principle. They use the many multiplet method there, they just don't call it that. How do we get off this now? Let's go back. Okay, so the question then is, can we use stars as our probe in our galaxy of alpha variation? I mentioned that we've already done this for 20 years using quasars. This top spectrum here is the best quasar spectrum for measuring alpha variation or probing alpha variation. It has a very high signal to noise, a very bright quasar. And look how many transitions it's got. It's got like, wow, 5 or 6 or 7 that you can actually use to probe alpha. Now that's great, but look how many you have in a stellar spectrum over the same wavelength range. You've got thousands. So for a long time, decades, many decades, people have thought, can we use stars as a probe where we have this huge statistical advantage? And by the way, you can get a lot more photons into your spectrograph from a star because they're typically brighter in the sky. Here's just a tiny little wavelength region, 10 nanometers, where you've got, you know, again, more transitions that you have available for your quasar spectrum. And look how similar they are. They're all similar depth, nicely spaced from each other. You can easily identify them. Seems like a perfect system to measure alpha in. Well, yes and no. The reason, well, okay, can we use stars, is the question. Yes, this was done a few years ago by Hees et al. They took Keck spectra, 10-meter telescope here to get this kind of ratty spectrum. Why? Because it's an infrared spectrum of a star that's very close to the galactic center. They were trying to probe alpha in regions of different gravitational potential, but of course the dark matter density will be different there too. And they managed to identify a whopping 10 lines from this spectrum where they could use the many multiplet method. And they compared those, the relative separations between these lines to what we know exists in the lab. And they got out a constraint on delta alpha and alpha of, you know, roughly 10 parts per million. Pretty good going, especially for the first time this was ever done. But you notice that this is the first time this was ever done, but only a few years ago. I mentioned that people have been wanting to do this for decades, but haven't. Why? Well, it's because if you have anything but a ratty spectrum like this, there's enormous systematic effects in stars. And we know, I mean, probably I don't have to tell many people in this audience at this institute why that is. Stars have all sorts of interesting astrophysics. From a fundamental physics point of view, they're a complete mess. There's fundamental physics, if there's any fundamental physics buried down in here, there's a whole lot of astrophysics you've got to solve or remove somehow before you get to that fundamental physics. There's convective cells that shift and provide asymmetries in the absorption lines. There's rotation, there's magnetic fields, there's flares. There's planets going around them. There's all sorts of stuff that you don't really want to know about if you want to do a fundamental physics experiment. Here's one example. This is what happens to absorption lines. This is the same absorption line simulated by Dravins for different stellar parameters, different metallicities, surface gravities, and temperatures of the star. And this asymmetry that you see to these lines, the shifts away from zero velocity that you see, are all due to the convection in the photosphere, right? The light coming that you see is predominantly coming from these cells, these upwelling cells that are actually moving towards you. So you see these blue shifts, and those blue shifts are a function of the depth at which those lines arise in the photosphere, and so you get these asymmetries as well as blue shifts. Those systematics alone limit you to precision of about 10 parts per million in delta alpha and alpha, and that's the kind of magic number that Hees et al. Got to, about 10 parts per million accuracy. And they can't really do any better than that. Doesn't matter how high a signal-to-noise spectrum you obtained from that star. That's what you're limited to because of this effect. But we think we can get around this, and when I say around this, I mean suppress these effects by a factor of 1,000 by using a differential technique, not comparing our spectrum from the stars to the laboratory, where all these shifts and asymmetries are not in the laboratory, but they are in the star, but by comparing the stellar spectrum to another stellar spectrum, but for stars that have very, very similar physical properties, right? So stars, although they're very complicated, at heart they're quite simple. The spectra the spectra of two stars that are very similar, have very similar properties, will be very similar, and that's the idea. So what we'd like to do then is say you collect a local reference sample of stars, and you compare those to a distant sample of stars, but they've got to be very similar types of stars, right? And by doing that, you can say, well, I'm looking for variations, differences in those distant star spectra compared to the local reference spectra, if you like. And this is a differential in a couple of other ways. What you're actually going to do here is look at, for star A and star B, the separation of pairs of lines. And you can make those very closely spaced pairs of lines to avoid sort of instrumental systematics as well. You look at that separation in star A, and though that separation is governed by the Q coefficients, the sensitivities to alpha variation for these two different lines. Same transitions in another star, but a different separation tells you that there's a variation in alpha. And if you can calculate what delta Q is, then you can actually say what the variation in alpha is between those two stars. You can't say what it is compared to the Earth, but you can say that those two stars have a different alpha. You've shown the same thing. You've shown that alpha varies. So this is really what we want to do. That's the stellar twins approach. We wanted to test this out first. I mean, we didn't know how well this would work. We wanted to test it out on the best possible data set available. And luckily, we don't have to go out and observe that data set. It already exists for this exquisitely well-characterized spectrograph called HARPS on the 3.6 meter ESO telescope in Chile. It's mounted in vacuum, it's very stabilized, it's very high resolving power, so you can look at your lines in detail. It's probably the best characterized astronomical spectrograph that we have ever built. But the most important thing is that it also has an enormous database, publicly available, of Sun-like stellar spectra. Why? Because it hunts for planets. And so it takes spectra again and again and again and again for years of the same set of stars. And they're largely Sun-like. And so we decided, well, let's look at solar twins to start with. Twins that are very much like our Sun, but also very much like each other in this database. And there's heaps of exposures where we could do this. This is just an example of two of them, two different stars. They've got HD numbers, so they're very bright. But you look at that top panel, and still only a very small part of the spectrum, you can't really tell the difference between those two spectra. I've deliberately offset them, otherwise they'd sort of just be hiding, one would be hiding behind the other. So they're very, very similar spectra. Here's two transitions that we've identified. We know the Q coefficients for, those sensitivities to alpha variation, and we can measure their separation here. And for one we get this number, and the other one we get this number, and those two are actually indistinguishable. The error bars on those overlap. So basically, those two separations for those two stars is the same. This is telling you, okay, this is a good measure of alpha variation. Now here is a point where I could have included another 5 slides and taken up probably 20 minutes explaining a whole bunch of details you wouldn't get. Just like with supernovae, they're not standard candles, they're standardizable candles, right? You can measure their luminosity, but that isn't the actual, you have to actually make some corrections to that luminosity to make it a standard. Similarly, with this velocity separation of this pair of lines, and all the pairs of lines we use, we have to standardize them. We have to look at how they vary with a few other phenomenological parameters, like the stellar parameters of the star. They do vary weakly with those parameters. So we can compare stars that are not quite the same as each other, don't have quite the same surface temperature or gravity or metallicity. That's actually a good thing that we can standardize that out. And we know how to do that completely phenomenologically. We don't have to have a model or any theories for that. We can do it completely empirically. So once we do that standardization, we get these results. So this is just using 17 stars, including our sun. Here are they, all the different stars. And it's also important to realize we're only using 17 pairs of transitions. It's actually 22 transitions, makes 17 pairs in this case, where we actually know the alpha sensitivities, the Q values. We use a whole bunch of exposures from HARPS, and we derive, look at the velocity separations of those 17 different pairs of transitions, and we're able to convert that into a delta alpha and alpha measurement for each star. And what you notice here is that we're talking about parts per billion on this axis. We measure here, what you're looking for here is, are these stars, do they have significantly different alpha values? And none of them do. They all agree with each other pretty much within 1 sigma, except for maybe 1 or 2 examples. The distribution of chi-squared there, even though it's only 17 points, is fine. You wouldn't say that there's any evidence for variation in alpha there. So what we can say is that in our very local universe, where these very bright stars are located, there are no variations larger than about 50 parts per billion in alpha. And if you take them all together and say, well, now I've got a local reference with which I can use to compare to more distant stars, that reference has a precision of 12 parts per billion. So we're way down now. The systematic errors in our measurements are they're at the 11 parts per billion level. Not 10 parts per million, 1,000 times lower by using this differential technique. So I think that's a huge success. I actually wrote in a grant application, this is what we do. It actually came true. Has anyone ever written something in a grant application where it really came true down to within a factor of 2? I'm really amazed how well this works. And so this has actually made us think that we can push this technique much further than we thought we might have been able to do before. Firstly, we want to go and start looking at more distant stars. And we started to do this using another spectrograph called Espresso on the Very Large Telescope in Chile. Much larger telescope, 8 meters. Now we can look at much fainter stars. So take our sun further away, it gets much fainter. We can look at it with this sort of super HARPS. And we can apply the same technique. So we've already observed about five solar twins. We've maybe got a couple of others from the archive, up to about a kiloparsec closer to the galactic center. Not a kiloparsec from the galactic center, a kiloparsec from Earth towards sort of closer to the galactic center than us. And we've got a whole bunch of these local twins as well to sort of cross-calibrate HARPS and Espresso so that we can actually do these measurements without observing another large sample of stars like existed already with HARPS. You can see in this bottom panel, it's one of these distant stars in the orange, one of the nearby well-known solar twins. They're basically identical. That means we're selecting these more distant twins really well. And we know that we can measure the separation, the velocity separation of a given pair of lines in those local twins, and just an example distant twin here in the same way. What you'll notice is, of course, the error bars are much larger for the distant twin because the signal-to-noise ratio is lower. Basically, for all the distant twin measurements we're going to make, the size of our error bars will be completely determined by how long we look at it, how long we can afford to look at it with the telescope, the photon statistics. Systematics are way, way down at the 11 parts per billion level. So we know we can use this technique with these more distant stars. The problem is that, of course, The sun, if you take it 8 kiloparsecs away or 7 kiloparsecs away towards the center of our galaxy, it's way too faint to see with these spectra. These are even the 8-meter telescopes that we have available. So we need a much brighter star. And the success of the solar twins has really taught us that we can push this technique much further, and we think we can push it to a type of giant star called a red clump star. So these are helium core burning red giants. They've gone through their, the helium flash. They're burning helium in their core, and because they're large, they're about 50 times brighter than the sun. So now we can actually start to see them at 7 kiloparsec distances with our existing telescopes and spectrographs. And the big question is, of course, well, can they be used to measure alpha? And we can do exactly the same thing, it turns out, that we did to prove that the solar twins work. I didn't think this would be true, but there is actually a large number of these observed with the same spectrograph HARPS. I actually still don't really know why someone's observed so many of these with HARPS. It's about 150. So we have a very good local sample of red clump star spectra from the same spectrograph that we used before. Here's one of them, a huge forest of lines that you can see, lots of opportunities there to measure alpha variation. Here's the same couple of transitions that I identified before in the solar twin. Here is the same separation between those lines. Again, we can use a large sample from HARPS to standardize this velocity separation and use it as a measure of alpha variation. And if we just look in this example at one pair of lines, we haven't measured alpha variation yet with this technique, but all we need to do is show that for the same pairs of lines, if we go through this standardization process that I've called model here and look at the velocity separation, the deviation from that model as a function of stellar parameters, one of them being metallicity, for example, we see no deviation and no evidence that some stars deviate from the others. These are all stars within about the local kind of 200 or 300 parsecs. So this is already telling us that you can use red clump stars in exactly the same way we used as solar twin stars before. This is the full metallicity range that you can have available for red clump stars. They cannot be lower metallicity than this. They also can't really be higher metallicity just because there aren't enough metals in our galaxy to have produced ones that are that metal rich. But if you go to much lower metallicities than this, you don't actually produce a red clump star from the stellar evolution tracks. So this is telling you that all red clump stars can be used for probing variation in alpha, no matter what their stellar parameters. They're all quite similar to each other, but they do have variations, and you can see that here. But it doesn't matter. We can completely standardize all of those red clump stars to use as a probe for alpha. So we're really excited by this. I did not expect that this would be true, but it works a treat. So we've gone and targeted some fields near the galactic center now because we really want stars not just 1 kiloparsec away, but 7 kiloparsecs away we think we can get to pretty easily. We don't want to look directly at the galactic center here at longitude and latitude 0. This is a map of the dust extinction, or actually the reddening probably in our galaxy. It's worst here, of course, so you don't want to target there. That's hard work. We've seen how ratty a spectrum you get from Keck in the infrared if you do that. Instead, what we do is we target fields a little bit off the plane where there is little pockets of low dust attenuation, but still as close to the galactic center in projection as possible. So we're balancing the dust reddening and dust extinction effects with how closely we can probe the center of our galaxy and the highest dark matter densities. Thank you. And to add to Espresso, that's on the 8-meter VLT in the south, last year was commissioned the Keck Planet Finder, another vacuum spectrograph that's stabilized and well characterized, well calibrated, now in the north on the Keck telescope on the 10-meter. So just a point, this is the same usual thing, a grating, big vacuum chamber, yeah, but this is interesting, this material here is 0 Dürr, which is what they make the backs of the mirrors for Keck out of and other telescopes. And this has basically a 0 coefficient of thermal expansion. So you put this in a vacuum chamber, even if you get small variations in temperature, you don't start shifting the items around effectively on this optical table. So it's a bit of an innovation there. But we can use this spectrograph, and indeed 1.5 weeks ago we did, for the first time. We've used the KPF just in early August to observe 5 red clump stars to start off the distant observing campaign for this project at 4 to 5 kiloparsecs, and we obtained higher signal-to-noise ratio than we thought we would because we had better seeing than we thought we would get. Turns out the exposure time calculator for this is really precise, so we know exactly what signal-to-noise ratio we're going to get for a given observation if we know the seeing. We also got some local reference stars. Some of them have enormous signal-to-noise ratio. I got close to saturating the detector, which I would not have been popular for, but we got really great spectra. Here are some examples just of single exposures now, not the total signal-to-noise ratios that I'm showing up there. The local star in orange this time, in the foreground, and the background one in blue is a red clump star at about 4.8 kiloparsecs away. So we can start to build up a sample now, which is going to populate that diagram that I showed you at the start of the talk. So here, what we think we can do now is we can easily project the uncertainties that we're going to get because they're just photon statistics. The systematics here are shown for the local sample. They're tiny. The uncertainties on these distant objects are easy to project because they're just photon statistics. And with 70 hours of telescope time split between 2 telescopes, the VLT and the Keck, we think we can get to these uncertainties here, which in total, if you bunch them all together, instead of in 3 bins, you'd get about 100 parts per billion precision. So it's about, we're getting down to now hundreds of times better precision than what exists already at similar distances. One final opportunity there is for the same spectra. I've told you that there's a bigger opportunity. There's lots more transitions available than what we can calculate the Q coefficients for. We only have 17 pairs at the moment. There's thousands of lines there that potentially we could use. The problem is that the lines we've chosen so far they only involve low energy levels. And those are the ones where you can actually point to them and say, I know the wave function of that orbital. I can tell you what orbital that is. And so I can write down a wave function and I can calculate a Q coefficient. Turns out that most of the transitions we see in stellar spectra are from most of them involve high energy levels. And that means there's a high density of states when you get up to these high energies, very small spacings between the energy levels, and you get quantum mechanical mixing between those levels. So you cannot say, and you cannot use your traditional approaches to calculating things from wave functions because you cannot define a wave function for those orbitals. There's a statistical distribution of wave functions. And it's impossible to calculate the Q coefficients for them all. But there are some techniques that have already been applied to plasma physics in this sort of level-resolved statistical theory where you have this quantum chaos regime, this high degree of mixing between huge numbers of transitions. And so instead of getting a Q value, you should be able to get a distribution of Q values for a given transition, a probability distribution of Q for each transition. And so if we can do that, then we actually have at least 500 more transitions available, right? At least 500 more pairs, probably more. And so we'll have a factor of 5 at least gain in sensitivity from the same spectra. You don't need to observe any more spectra. This comes for free if you can calculate these Q coefficients. So you get not 100 parts per billion precision now for your distance sample, but 20 parts per billion. I think that's probably the limit of where we can go with this technique, but I can still be proven wrong by this technique. It's been good so far. But we can get down to that precision level and really perform this test of fundamental physics at these sorts of precision levels in astronomy. So I think that's pretty remarkable. So I'll finish up. Just want to conclude that I think stellar twins really can test whether there's a connection between alpha and dark matter density in our galaxy. This is it's a completely new test, right? It's pretty cheap. You don't have to build a particle accelerator or any labs. You have the telescopes there. You can just use some of the observing time, which itself is not cheap, but it's not much observing time. It's a new and pretty cheap test of fundamental physics in a parameter space we've not really touched before. It's going to be 500 times more precise than the existing constraint. Right? We have all the technology we need to do this. We've just got to actually do the work. We've shown that this works with solar twins. We know that there's no variations locally more than 50 parts per billion. We've shown from HARPS again that red clump stars do work with this approach, and so it is we can do this work with espresso and KPF to get these distant stellar spectra, and actually if we can get about 70 hours split between these two telescopes, first, even without doing any quantum mechanics, we get down to 100 parts per billion precision. And if we also do the quantum mechanics, we get a factor of 5 improvement. So I think that's pretty remarkable, and I'm hope to come back in 3 years and tell you whether we got to that plot or not. So thank you.
Showed in the beginning that alpha is like E squared on h bus, and we have other measurements of like speed of light individually, but if the structure constant is variable, what aspect, like which part do you think is the part that is variable? Is it like speed of light, or is it like...
Yeah, it's a good question, and the answer is murky. So you have to realize that we cannot really measure variations in any quantity that has units. You can only measure experimentally variations in things that are dimensionless. The key point here is that C and E and h bar are all part of our units system. So you can't then say, actually you can't measure variations in the speed of light because it's now defined. Why is it defined? It doesn't make sense. It's a physical quantity, right? It's defined because it's part of the unit system. So actually, the only thing you can really test experimentally is whether alpha varies. Similarly with G, big G, you have to combine it with some other fundamental constants which are part of the unit systems for mass and other things in order for that to make sense. So you can write down, if you're careful with your units, you can write down theories that are varying C theories, for example, but every one of those theories has a corresponding, probably much more mathematically complicated, varying H bar theory or varying E theory. They're one-to-one. It's just that the maths for one might look a lot simpler, and conceptually might be simpler than another. So it's not a very satisfying answer, but that's the answer that I probably can't give you much more detail than that, but that's the answer that is correct. But going further into those unit systems and explaining that in more detail, I'm the wrong person.
Great talk. I just have a question. So, like, how do the analysis with red clump stars compare to the solar twins? Like, especially the local sample in terms of their systematics. I mean, do they introduce them more systematics, or they are more or less the same value?
We don't quite know the answer to that. Certainly, it's not very different. We don't see evidence of, at the moment, even detectable systematics in the analysis we've done so far of the local red clump sample. The local solar twin sample is very well characterized, and we know that those systematics are at the 11 parts per billion level. In velocity terms, for an individual pair of lines, it's at about the sort of 0 to 15 meter per second, roughly, systematic errors. And they might come from a range of astrophysical things or potentially instrumental systematics as well. We haven't done that full analysis yet for the red clump sample. The reason we haven't is because we're trying to, I glossed over the fact that red clump sample is probably not pure. There's probably some red giants in there that are not the first descent red giants that just happen to have stellar parameters that are like the red clump stars. And so we can't tell from the results. They don't stand out as outliers. Clearly, we may not need to separate them out, but we are actually trying to separate them out with some existing spectra of stars where the evolutionary state is known. Are they a red clump or a red giant? Separating those two samples has been traditionally difficult, but now we have spectral signatures that allow us to do that. So that's why we haven't gone to that full analysis yet. But we don't see anything obvious. You can tell from that plot that I showed, the one with proof of concept on it, there's no big scatter that goes beyond what you'd expect from the error bars alone.